Thank you. Thank you so much for the beautiful introduction. Um, yeah, so I'm really happy to be here, and thank you everyone for coming despite it's a summer vacation. So the topic is about contraction theory. Then how many minutes do I have? 45. 45 plus. Okay, perfect. Yeah, the topic is about contraction theory, and I will try to give you a introductory overview of contraction theory with a little bit of applications, and also I'm gonna focus on why we need a contraction theory, even why we need like mathematical guarantees and so on, and try to connect that with our newer kind of research field we'll be pursuing with more um, is something of intelligent control systems, meaning data-driven control and learning-based controls. So let's see if this works. Okay. So this is one of the representative project we had with contraction theory, and this is about data reference. So you can see actual one at the very bottom. So this is the trajectories you see here, these yellow curves and the pink curve is kind of hard to see. But anyways, these are the trajectories of what we call interstellar objects coming outside of the solar system to visit us. But one of the biggest challenge here, so the point is the mission here is that we have a spacecraft and we want to intercept them because the interstellar object kind of have some materials outside of the solar system, which is so hard to get. So we want to explore them, but the biggest challenge is that it's high speed and also it's kind of hard to detect, meaning it has a significant answer compared to more significant compared to like conventional missions. And these yellow balls kind of represent the big uncertainty. And how do we make decisions? Meaning how do we make optimal thruster, decide optimal thruster values under this significant uncertainty? That's a challenge. And this is just me showing some empirical results. So we also we kind of developed some algorithm and we tested this on board, and this kind of looks rudimentary, but what's happening is there is that you have a spacecraft like a simulator with like actual thrusters, and what we are doing here is that we are injecting like a significant state uncertainty to the system, so they have to figure out their uncertainty, quantify their uncertainty as we go, and use that quantified information to make decisions. So as you're not kind of now imagining, the contraction theory, control theory, is about the decision making under uncertainty. How do we make good decisions under various types of uncertainty? So that's kind of like the topic he being interested in. So and then this is just another project, but now this is what's called the OMO, one of the interstellar objects coming outside of came to the Earth back in like 2017-ish, if I remember correctly. But then if we are expecting a lot more in the future. And now there's another layer of uncertainty here if you move on to multi-agent systems. So you see like the heterogeneous spacecraft with like different roles, and then how do they communicate with each other, sharing the findings and making decisions in a distributed manner, right? Without knowing what the other spacecraft's going to do. And based on that information, how do you make a good decision? So there's several types of uncertainty like that, and constructing theoretically valid decision out of all these information is like what we do. So I'm going to talk about contraction theory mostly, but let me just briefly summarize what I just said using this figure. So I put it this is more like a generic view of what we do, not just contraction theory, but also control theory. So control theory, simply put, is that based on the model, we get guarantees. We have a system, and we get guarantees. The guarantees could mean robustness or stability, safety, things like that. You can say a lot of things in control theory based on kind of strong assumptions, right? And for in contrast, in like intelligent systems, I'm using this as a generic term, but this just means that the systems with some sort of like a machine learning tools, or it could be like data-driven approaches. So here, what we typically do is that we use like a lot of data to make a good decision. But the guarantees is kind of a casual, can be casual there. So how can we connect these two fields so that the intelligent systems will be equipped with formal mathematical guarantees? So one way to do it, although this is not the only way, one like a systematic way of doing this can be a contraction theory, but it's just one of them. And as he said very beautifully, we have a tutorial kind of papers and all the materials if you Google my website. So please, if you are really interested in mathematical details, you can actually refer to that. And I'm trying to cover the basics of math at the later part of the presentation. Okay, so now we are kind of hopefully motivated to look at the contraction theory and what is that even, right? So the contraction theory is, as you can see here, actually not yet. So we have, let's say we have two systems. This star basically represents a system. And the one at the top is your ideal, let's say it's an ideal operation in a like ideal condition. And over there, you have another star, which is your current, representing the current operational system. So this is a super kind of abstracted figure, but that system over there wants to go up to the top. And the contraction theory is basically about defining the distance. So let's define a distance as the altitude, right? I mean, that's probably the simplest way of defining the distance. But if you look at the downhill, I mean, this is kind of like a gradient ascent problem, right? If you know, like a gradient descent, ascent kind of algorithms, machine learning. But anyway, at the downhill, this distance is confusing, right? The going up, in order to go up, going downhill is the only way. But the altitude, the distance we just defined, is increasing. Although it's making a good decision, distance is increasing. So it's confusing in a sense that they may think that they're making a bad decision even when they're actually doing a good decision. So let's change the way we define the distance, and this is probably too obvious. But let's change the way we define the distance, and that's what basically contraction theory does. So instead of just defining the altitude as a distance, like basically state-independent distance, you could define a distance in a way that is state-dependent. So you could define a distance, you could basically define a local coordinate as if like mine. You can define a local coordinate like this, and you can view the direction of the lead arrow as the distance, the way to measure the distance. And you can now see that the distance defined in this way is decreased along the curve. So this is super naive, intuitive example of to imply the importance of defining the distance. Either way, as if you're making a good decision, your distance should be telling you that you are making a good decision. So that's like the core of contraction theory. Nothing complicated. It's just about defining a distance. It's all. So, graphically speaking, you have again, you have two systems: the ideal performance, current performance. There are like several different versions of contraction theory. I will be just talking about one of them. but you have two systems. Let's say you have two systems and you want to measure a distance. The easiest way could be altitude. The other easy way in robotics is like a Euclidean distance. You just measure the distance in the flat surface. But what's the best way to measure the distance so that the distance measured in that metric will be decreasing as a result of good decision making? That's analysis. And then another thing you could do is how can we derive such a decision-making policy that your defined distance is decreased? So this is kind of like a simultaneous problem. You define a distance for analysis and for controlling something. And yeah, that's contraction theory. And by the way, if you have any questions, feel free to ask any time during my presentation or at the very end. I don't mind at all. So going back, this synchronicity is coming from the origin of contraction theory. And as you might imagine, contraction theory, if you go back, it's basically a contraction mapping. So Banach, you probably know the Banach's contraction mapping theorem, right? At some point in your career. So contraction mapping basically tells you that if you have like a mapping in a complete matrix, whatever space, your sequence, I'm going to show you the equation, that it converging to something. And the reference point will be unique, is what we have with the contraction mapping theorem. And then it was used for analyzing the stability of like a numerical integration in your system, and that's that. And there was some like computational applications. I kind of implied the connection of this was gradient descent, gradient ascent, but this computation work is about using this kind of concept for analyzing the stability of the new Newtonian kind of method for solving the nonlinear equation. And then system state control. So this is mostly the contraction theory I'm going to be talking about today. It's a contraction theory primarily used for analyzing the dynamical system with some control input. So instead of just analyzing something, although this original paper is about the analysis, instead of just analyzing it, how do we control it so that you can have some desired property? And this is like a super intuitive basic equation we have in contraction theory. So it's just a way of designing the distance. So we naturally think of a metric space where X is like whatever space you're in. It can be just a Euclidean space, and you define the distance. So D can also be a Euclidean distance. For example, if you know a Bellman equation in like reinforcement learning, this D can be the infinity node, right? Actually the Bellman operator is known to be a contraction mapping. But anyway, we define an operator that maps from something in your space to something else. And then you can see that the distance between them is decreasing. So this is basically the equation you need for contraction mapping. As in the distance between 2 points after the application of your operators will be decreasing by a factor given by C. And if C is less than 1, we can say that this is a contraction mapping and it has like the nice properties, right? The uniqueness of the equilibrium point and so on. And this is basically the origin of contraction theory. And you can see the similarity to like ellipsis types of condition, right? If your C is like greater than 1, this is basically kind of saying that this mapping is ellipsis. So it's kind of a stronger version of ellipsis continuity. Anyway, that's that. And now I'm gonna take a little bit of detour right after this, but there's for introduction. Contraction theory I'm gonna talk about today is differential abstraction of contraction theory. Do you guys know the Lyapunov theory? How many of you know the Lyapunov theory? Right, okay, most of them know the Lyapunov theory, which is good. The Lyapunov theory is a version of contraction, right? It's like you have a energy. So now we are talking about dynamical system. We have x dot is equals to f of x. And the Lyapunov theory is basically about finding a Lyapunov function v that decreases along the trajectory. So this is a very, very nonlinear concept in the sense that you use a nonlinear function and you use PDE to find the v. But what if we can just look at the differential, like a small region of your dynamical system? That's why we have like delta here. Let's look at the tiny region, and so that we can kind of reuse the linear systems type analysis in constructing a Lyapunov function, so that we can use a little bit more general approaches to the synthesis of the Lyapunov function. So that's what I mean by differential abstraction, and hopefully I will touch on to this a little bit more later. And yeah, there's actually one more, but the contraction can be everywhere. As I implied, it could be about asymptotic stability, as I was saying, that Lyapunov in contraction mapping sense, the Lyapunov function, the analysis is about getting asymptotic stability in the system, and that can be viewed as a version of contraction. And incremental stability, this is a different concept in stability, which basically says that if you have like 100 different trajectories for your dynamical system, and incremental stability basically says that all the trajectories converge to one. And we don't care about that trajectory. We will be converging. It just says that it converges to one, right? It can be like whatever. So it can be exponentially diverging trajectory, right? It's converging to something, but that trajectory can be divergent. So synchronization kind of concept. And the safety, which is, if you know barrier function, which is known to be a dual of a Lyapunov function. And what it basically does is that you try to converge your system to a safe set, so that your safe set is going to be for invariant. And I can keep doing this, but for the sake of time, I'll just skip optimality, Bellman operator, right? The contraction mapping, the gradient descent. Do you have like a dynamical system, and you can analyze, do the same thing for analyzing the convergence of the gradient descent algorithms with like convexity and so on. You can also prove the stronger property like optimality. And numerical integration, leachability, as I mentioned earlier, this concept has a similar structure, dynamical system plus some sort of convergence. So what I'm trying to say here is that as long as there's some sort of like a convergence, contraction theory in the broad sense could describe such phenomena. And the 7 violet has a question mark, meaning this is like the future work. But if you think of an alignment of your like AI integrated system with your kind of an ideal behavior, like ethical behavior in AI, so this kind of convergence process can be viewed as a contraction if we can properly model the dynamics and define the metric. So this is already a clearly a bold statement, but contraction might be a dynamic. If you have a dynamics, it could be a dynamically intrinsic concept in analyzing the convergence of that system and in providing mathematical guarantees for these systems, including those with data-driven tools, which will be the topic later. But yeah, do you have any questions so far? You good? Okay. So now this is one of my favorite movie. A lot of things on my experiment. And that my point is, why do we even need contraction? So here, what's happened is that this is a challenging problem, as you probably know. You have this is me trying to solve the multi-agent motion planning problem in a distributed manner. meaning each of the agent has access only to the state of agent around it with a limited weights. And then they have to basically make decisions based on that. And this is a highly nonlinear problem. And you don't have a global solution, unfortunately. So what I did initially is let's just use a neural network where you can approximate like a nonlinear optimization problem kind of easily, right? I mean, at least you can learn something. And then let's implement that controller on actual hardware. But this is actually what happened. Thirdly, because what we call the simple real time, right? The dynamics I used for controlling these guys are different from the dynamics of the real world. And also the information you get from the surrounding agents can be different from the actual information you get from the real world. These kind of discrepancy accumulates, and then it's stopped operating. And this is like what's called a crazy price, the cheap kind of drawn. So it's okay, we can just replace it. But what if this is like a spacecraft, right? If you have like tens of spacecraft in space and this happened, right? Then that's going to be a catastrophic failure. So that's part of the reason why we in like especially in aerospace kind of domains, that's part of the reason why we appreciate the mathematical term. This is another example. You can ignore the one on the left column. This is kind of unrelated. You can just look at the left column. So, do you guys know the three-body problem? The sum, yes. Okay, right part, yes. The three-body problem is basically you have three objects affected each other by the gravitational field. So you have like a gravity force between them, and that creates what's called a chaotic. This is actually a restricted three-body problem in a sense that one of them has a significantly smaller mass compared to the other two. So we have the Earth, Moon, and the spacecraft as a three-body, and they are affecting each other through the gravity. And it's chaotic, meaning that the small initial state displacement will be magnified significantly. So it's kind of small and hard to see. But this is a ground truth trajectory of the chaotic system. You have, if I remember correctly, we start from and we basically all of them has like this very similar initial condition. We just add a slight bit of manipulation at the and we propagate the dynamics. And because of the chaotic nature, the final results, final trajectory at the very end are vastly different, right? So let's do like something similar as I did in the drawing experiment. Let's just approximate this using a machine learning tool. And here we use the transformer, which is kind of getting more and more popular these days because it's used for like a chat GPT, like whatever reinforcement learning algorithms and so on. So let's just use it. And here's what happened here. And these are the three represented trajectories. It's maybe easier to see. And you can see that this chaotic like orange curve represents the ground truth. So this transformer is supposed to track this exactly, but you can see that it's not happening, right? So that's part of the reason why if you use a data-driven approach, is just naively without thinking about the consequences of like uncertainties and disturbances, you just cannot do it sometimes. This is kind of an extreme example because it's chaotic, but this is a kind of my way of showing the intuition of why these kind of properties, mathematical guarantees can be even practically important, not just for your like safety. And then this is, I'm not going to talk about the details, but let's just infuse a contraction kind of notion. During the training, let's infuse a contraction kind of notion in the loss function. And then just train the same thing. And with the same amount of information, that's like dot you can see here, it's a context. Here, just give it this kind of context to the transformer, they will propagate the dynamics. And then with the same amount of the contextual information, they almost perfectly reproduce the chaotic trajectory, right? You can see the overlap between the orange curves and the purple lines. The reason why is because in training, they will learn to be robust against these disturbances. So this is kind of the intuitive experimental results why we care about the contraction, or at least robustness. Yeah. What are they? Yeah, so this is kind of I copy and pasted some record materials from different things. So this is just foundation models and board models. So here I was I was introducing this kind of things for foundation model. I just realized that it's still there like right now. But I will talk about that at the Bertardi variant. Yeah, thank you for the question. So, and so yeah, still about this question, fraction necessary. There was different situations, right? Like a lot of my students, postdocs, they are doing robotics, and in robotics, this is all the uncertainty disturbances. They are always there. The biggest one is called the sim-to-real gaps, which is basically just a simulation to reality gap. Meaning, in robotics, sampling data is can be expensive, right? Because in order to get like 100 trajectories of your robots, you basically have to do like 100 experiments, right? Doing that, if you think of doing this in space, sampling like 100 trajectory with your like a new space robot, that's unrealistic, which is why we use simulations, virtual environments to sample data and use these data to train your control policy, to create a guess of your model, and so on. But then sim-to-real gap could act very in a bad way, as you saw in the previous experiment, right? The sim-to-real gap could accumulate as your trajectory propagates. And if your underlying dynamics is chaotic, this accumulation, this small perturbation will accumulate, make the system diverge. So these things could happen. Learn policies and models. If you learn your neural network model is learned fully, then that can also act as a disturbance, uncertain. And you could it could happen that the dynamics is just like chaotic, and it's could be very sensitive to perturbation. And what else? Yeah, and there could be like a sensing actuation, kind of a sensor noises and so on. But my point is that maybe contraction is not a necessity, but at least being robust against all these uncertainties and disturbances, perturbations can be a necessity. And that's the underlying motivation in why we are kind of emphasizing having a little bit of control theoretic perspective in data-driven systems, modern like intelligence systems. Okay, that's probably enough introduction. So let me talk a little bit about the math, so I can introduce you to the field of what's going on. And we are currently pursuing these four, I mean, roughly speaking, four directions. The first one, this is probably what you're familiar with from classes. Robust control, robust nonlinear control. Let's assume that you have a system with a bounded uncertainty. And what's the performance you can prove for these kind of systems? That's a classical topic of like robust control. And then second, yeah, I should have talked about this one first. So let's decompose your system into two parts, known parts and unknown parts. And the nominal model, this could be given by your like machine learning model. It could be given by your prior knowledge of the system. It could be nothing, right? It could be completely data driven. Then the uncertainty dominates these. But anyway, you have two parts, and then the first one is the case where the uncertainty is bounded. And the second one is uncertainty is stochastic with a known distribution. This is a classical stochastic nonlinear control topic where, for example, people often assume that the uncertainty is Gaussian distributed. And then the third one, which is slightly difficult, is more difficult, is statistically robust nonlinear control. This is what we were doing like the last 2 years. The uncertainty is an uncertainty still, but that is not bounded, or we don't know the distribution. Or more like we are not going to assume that it's bound. We are not going to assume that we know the distribution. We know we have access to the data of your uncertainty, and let's use this data to quantify the uncertainty so that we can use the previous. And the final one is statistically adaptive nonlinear control or statistically stochastic nonlinear control, like whatever. We don't have a term yet. And this is where this is the most challenging setting where we sample data and generate the control policy simultaneously. We quantify the uncertainty as we go, and we at the same time design the control policy. So that's why we have it adaptive here. And initially, you may not have any like guarantee, right? If you don't have any data of the uncertainty, and if you're just if you just have a nominal system, then providing guarantee is probably impossible. But then, as you accumulate data, what can we say about this right guaranteed robustness and stuff? Is probably the most challenging situation, the scenario where we don't have an exact answer yet. Well, let me just put it here. And this is an outdated figure because I don't have a case 3 and 4. But anyway, I have a case 1 and 2. And you get what I mean, right? You have a bounded disturbance, capacity disturbance. And if you can quantify these bounds using like data, you can also say something that you can reuse the classical control results for doing these kind of things. Okay, technical details. So I definitely don't have enough time to talk about all the technical details, so I'm going to skip equations like a lot. But if you're really interested, I have a lecture, like a couple of lecture notes, not all of them, made available online. So basically, search from contraction, and then we can we talk about the statistical inference with like some basics and with a little bit of proofs, and how do we combine them into one kind of a lecture. There's some homework if you want, if you're really into it. But the things I'm going to talk about from now on is basically from here. So instead of looking at the mathematical details, I would just try to cover the high level idea behind them. And definitely I don't have any time to talk about all these, but let me start with robustness. So now we have a dynamical system. This is probably the first appearance of the dynamical system in my presentation. So let's consider a dynamical system. I don't even have U here. But U can be this can be a closed system where U is already designed, let's say. And you have two types of disturbances. First, D represents the bounded external disturbance, the Bldg one. The C, or CPW, this is stochastic disturbance, which can be unbounded with some known distribution. In a process, basically, this is kind of like representing a Gaussian sort of disturbance in a continuous time sense. So this is just kind of a introduction to contraction theory work. And then this is what I was talking about. Instead of just considering the generic V, the nonlinear function, let's just consider differentials. So these like a tiny state, as in like a calculus of variation. If you know, if you learn like well, let's just look at this and define them. Let's change the problem finding B to problem of finding a matrix. And this is our reactive function, and this is a figure. Oh no. So this is just a regularity condition so that we know that the solution exists basically. Mass is not important, and this is actually what Sujin did, but we can also consider other types of disturbances for more general treatment of these analysis. Anyway, what we do is because we want to analyze the time evolution of this kind of a distance, right? If you remember, we were talking about distance, and B basically defines a distance. And we consider what we call the virtual system. And at the very beginning, we had a figure showing the distance between two systems, right? The ideal system and the current system. And now it's about trajectories. The perturbed trajectory represents the current, like actual state. And the x naught represents the unperturbed solution trajectory. This is kind of like the ideal trajectory. We cannot reproduce because everything is under observed. So quantifying the distance between them is originally what we do. And then we take the time derivative. So the reason why we have a very simple here is just because the dynamics is stochastic. It's basically a v dot, like time derivative along the dynamics to discuss the time evolution. And then I'm gonna skip the significant details. So this is again the visual picture of what's happening. Significant details, skipping the significant mathematical details. Basically, by computing the differential, the international differential operator, like time derivative, with this contraction condition, you get this equation at the bottom, which basically said that your distance is decreasing with slight bit of perturbation. This curve is non-vanishing, right? It's a decreasing curve, non-vanishing curve. And using this inequality, you get this is what we call the Dinkin's formula, and you get the in expectation, you get something like this. So the second term, as t goes to infinity, time goes to infinity, the second term disappears. The first term remains. And the first term remains because of the uncertainty. So basically the C term over there captures all the uncertainties coming from the stochastic disturbance or the bounded disturbance. Okay. So I'm not expecting you to follow the mathematical details. I want you to try to get the just high level ideas. Here. And then the learning based systems. Let's say now, as I slightly mentioned earlier, let's consider the case where F is just unknown. You just have a dynamics. You know that there is a dynamics, but you don't know anything about the dynamics side of scenario. And F2 is basically unknown. So let's, for example, use a neural network or like Cindy, the nonlinear dynamics approximation tools to get your model. And then, I mean, this is just as adding and subtracting the same term, but you can decompose the system to like this. And if you can enforce the contraction for the first term, you can basically treat the second term as an external disturbance. This is nothing complicated. And then under these assumptions, you can conclude the same results. And we are trying, and later I'll try to remove this assumption. But basically now you can quantify the distance between the learned system and the something that you care about. So this is the kind of a super quick overview of robustness, the guarantee I was talking about. The robustness is basically about the even when your system is perturbed, your distance between the ideal system
and non-ideal system will be bounded forever. So it could happen, right? As you saw in the chaotic systems, right? If even with like a bounded disturbance, your system's going to diverge. The distance between the ideal system and non-ideal system could become infinity. But the robustness is about is a statement that this is not going to happen. It will be bounded. And this is a nice property you should have in systems, like learning-based systems where your system is subject to perturbation and uncertainty. And similarly, using the stochastic systems control theory tools, you can prove the safety guarantees, which is basically just that we had here we didn't have any screamer, meaning that this bound holds at each time t. But if you have a screamer, this is basically a stronger guarantee, right? For this time interval, you will be safe, kind of guarantee. And using the stochastic control theory tools, defining a new like a positive function w, you can also quantify, provide some sort of like a guarantee for the streamum. This is just me saying that we have a stronger version of the guarantee. And yeah, one last thing for the contraction part is that the bound we were talking about, the C term we heard here, this term can actually be written as a convex function. So C term, for some reason, I'm using C1 here. But anyway, the bound of we had in the robustness can be expressed as a convex constraint, which is the very property you get from the kind of like a linearity of contraction theory. This is kind of like the whole reason why we started looking at the small space, so we can do things more computationally efficiently, right? Otherwise, why do we even care, right? And then we can formulate a convex optimization problem to, so all the results so far, we're assuming that we know the matrix function. But now here we are providing a convex optimization way to get these kind of metrics. Okay, yeah. So obviously, I think I'm already spending 45 minutes. Can I just get 5 minutes?
Yeah.
Okay, so there's obviously what's missing, right? Do you know what's missing? Any idea? I mean, yeah, there are like lots of things missing, but for the sake of time, let me just say it. So what's missing is the assumption, right? All the argument I did is based on assumption that we know something about the uncertainty, and it's actually contradictory to what I was saying. So assuming that this search disturbance is bounded, you have all the nice results. But is it bounded? Right? The nature of the uncertainty, it's kind of contradicting to the nature of uncertainty, right? How do we know that your uncertainty is bounded? So we need to use some information from data so that this assumption is true, so that you can use the results, nice, right? The control theory results we stated earlier. So this is again impossible to cover the mathematical details like right now. But again, yeah, this is unbounded, not assuming that it's bounded is unrealistic. And now let's talk about LLM. My student, one of them is actually Inyon sitting over there. She's doing like LLM based control. But if you use like LLM based control for your system, how do we know that your LLM is not going to hallucinate? And more importantly, if they do hallucinate, how do we know that we are robust against these hallucinations, right? How do we know that the hallucination is bounded? The only way to do it is through data. So let's do data-driven statistical approaches on top of classical nonlinear control theory is the transition we are making recently. And without knowing anything about prediction structure, right? You can use LLM, you can use neural network, you can use whatever.
and also the data distribution. The underlying this data distribution could be Gaussian, non-Gaussian. Let's just not care. And what can we say something about the uncertainty through data? Okay, so now one of the biggest assumptions we make is what's called exchangeability. So let's say you have like endpoints data. Let's permute the data. And then exchangeability basically says that the joint distribution of the entire data will be remain unchanged, which is a strong assumption we are trying to re-rux. But based on this exchangeability assumption, we can get a nice guarantee, which is this. Let me just move on to intuitive explanation. So let's say you have like a whatever approximator given x. So f is some unknown function, for example, your viewer phenomena, right? Stock plot of the viewer, and you have a neural network f hat that approximates the stock based on something. So basically what we want to do is to bound the distance between f and f hat, right? And then basically through the data with the exchangeability assumption, as I've been saying, this can be stock pricey, this can be the prediction of your dynamic system, this neural network, can be reinforcement learning policy, this your transformer neural network, or LLMs as they use. So we can, with some mathematical details, I'm going to skip, you can bound things like this. So what it's basically saying, this. What this is basically saying, so this is the uncertainty part. Previously, we just assumed that this is bound. But now you have some sort of direct weird alpha bound, which is informed by the. So you can kind of bound the uncertainty with data. And the price you have to pay is that now the bound is probabilistic. With certain probability, positive probability, your uncertainty can be bound. Is what this is saying. So finally, naturally, what we gonna do is let's use this with all the existing results of control theory, right? So we can discuss this kind the bound in a closed loop of the dynamic system. So that's what we did with conformal, what we call conformal contraction. And now going back to our example where f is unknown. And previously we assumed that the learning error of the prediction of the dynamics is bounded. But let's not assume that it's bounded for now. And let's use the same theorem. And now and with the same contraction condition. And then now what we get is this. So we get the similar type of bound without assuming that the uncertainty is bound. But again, the price you have to pay, two prices actually. The first is going to be finite time. Second, it's going to be probabilistic. But at least we can say something about the robustness of your data-driven systems with a realistic assumption that basically we are not saying that you know something about the uncertainty. We just know the data, right? So that's conformal contraction, and we did a Ryakhov. And we also did a barrier function, if you know. So this is a version of a Ryakhov function. This is kind of the reason why we are saying that this is dual. So this is for like safety, forward invariance of the system. And so on. So yeah, this is almost it for my presentation, and everything else I hope is just applications. We did this, this is just a simulation. We have simulation results. And as I said earlier, we have robots applications where we want to control robots is like machine learning tools, including like large language models, vision language models, word models, language models, all these kind of fancy AI models. These are data driven, and we don't know anything about the uncertainty, right? We are informed only by the data.
how can we prove the robustness of these approaches so that it will be operational in the system? And we did, and this is just a facility. And we did this with reinforcement learning, where the reinforcement learning introduced the additional source of data. And for some reason, one of the students tested this with a completely model-free approach. They just sampled the trajectory of the robots, like 20 trajectories. They just use this data to create a reinforcement learning control policy with contraction. If you just use a transformer TPO kind of approaches, it's not going to work. But if it's like a limited amount of data, because of the robustness, it works. So yeah, I guess and then we have like a non-Gaussian examples because we don't care about the distribution, right? We can do the same thing with for non-Gaussian distribution. So we did it. It's like easier version of the robots, and we did Koopman, and this is again going back to the sampling. Actually, this is it. But anyway, let me skip. And this is the project that I was talking about. Inyon, she was doing basically using the vision language models for predicting the drone's dynamical system parameters. But then we are also introducing uncertainty, right? So how do we deal with these types of stuff, and so on? So let me skip. I guess I have too many. So this is the one I showed earlier, and we have like theoretical analysis with reinforcement learning is a similar idea. And yeah, so anyway, yeah, that's basically it. Maybe before I talk about open problems, I can take questions, and if you have a few questions, I can talk about open problems. Does that sound good? I believe. So that'd be good too. Yeah, let me stop here and let me take questions first. So thank you for listening for now. And yeah, ask me questions if you have any. Yeah. Yeah. So yeah, that's a good point. Yeah, I'm mostly interested in Riemannian, the two-node kind of a metrics for computational simplicity. Because downstream, I'm thinking of applying this like robots and aerospace kind of systems, and generalizing it further to like different types of metrics. Yeah, that's an interesting question, but we haven't done. Yep. That's not binding. Yeah. Right. Yes. Decreasing of the load. Yes. 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 So yeah, I understand that what I not mentioned how to inform that information to the model by the simple solution. Oh, because you're talking the learning for yeah. I agree. Well, totally really. Yeah. Yeah, I see your point. Yeah, I skipped a significant amount of details here, so your confusion is valid. Basically what we do is we did a little bit of a trick. So unlike the Apple theory, the system is decreasing not to an equilibrium point, right? It's the system is converging to a single trajectory. So our loss function basically captures that, meaning in implementation, your system will not know the ideal trajectory, right? But because the contraction theory basically guarantees that all the neighboring trajectories converges to one. So in this region, there's a certain radius where we know that all the trajectory converges to one. So in the loss function, we kind of try to inform that in this radius, this is your ideal trajectory. So in the implementation, they don't need the ideal trajectory, but through the loss function, they can implicitly learn what your ideal trajectory is. But it's probably a lot easier if you look at the equation. Yeah. Yeah. Sorry. Yeah. Sure. Yeah. Yeah. Um, okay. So, yeah, that's a great question. Yeah, I see. Yeah, so the original notion of contraction, the differential one is independent of the ideal trajectory. So it's separate. Design ideal trajectory, whatever way. So if somebody else is doing a bad job designing an ideal trajectory in a bad way, then even if you're contracting to that, then you're just contracting to something bad. So it's kind of separate. So the ideal actually have to be just practice. Right. So it can be just a Turget system you define in a different way. But we are also, so this is kind of like although it's originally decoupled, we are trying to combine them together because as you said, what if your idea is not the ideal, it's just there, right? So how do we inform the feedback part of the design to make your ideal better? So that's more like an iterative process, like a higher level, right, feedback control. But yeah, no general answer. Yeah, thanks for a very good question. Yeah. Sure. Okay. Yeah, that's also a really good question. That's a limitation of exchangeability, right? How do you know that your virtual system is exchangeable with very real system? It's actually not. But so we still unfortunately, in order to apply the conformal prediction kind of ideas, we still need the ground truth. Meaning you still need to sample a little bit of the true trajectory. Otherwise, if so, basically, it's similar to his question. If we don't know the ground truth, like at all, it's very difficult to start discussing the guarantees. The guarantees we are talking about is relative. Contraction is relative, and also the conformal prediction is relative. So if your ground truth for both of the cases are bad, or we just don't have access to them, yeah, unfortunately, it's difficult. But that's why we are trying to be adaptive. So instead of initially, you may not have any like a good data sometimes, but as we accumulate something, what it would be the asymptotic, like the improvement of the guarantees, like for example, in iteratively refining the ideal trajectory. So you're kind of tracking trajectory like this. So ideal trajectory is also important. So how do we make things adaptive, right? How do we make use of online data to kind of address the challenge you just mentioned? So that's what we're trying to do. That's why we had I had an open problems in the title. There are like lots of open problems. Yeah. Yep. Mm-hmm. Right. Mm-hmm. Yeah, that's also a great question. Actually I have an idea. We have an idea, but it's in a proposal phase. So yeah, I can probably discuss online discuss offline. We have some ideas, but I don't have a concrete enough ideas to present yet, unfortunately. Yeah. But that's a limitation, right? It's probably it's not even like expectation. It's just the improbability this is what's gonna happen, which is weak. I still like the part where we can do everything with data driven kind of ideas, but yeah, it's that's a limitation, and some people don't like it, especially people in like aerospace kind of community where the failure is a super high cost. So we are trying to complement um, this kind of idea with slightly stronger deterministic ideas of the characters. Yeah, yeah. But thank you for your good question. Is there any other question? Yeah, please. Thank you. I'm kind of simple. But my question is question decision making. So that's what we are doing. Right. But can we actually avoid anything? Avoid assuming anything about uncertainty? And it's a philosophical question. Uncertainty, by nature, if it is uncertainty, there cannot be certainty there. Yep. Then it means there will be something always remaining. I still but are we just scratching by assuming something, assuming different for our uncertainty? Uh, yeah, I almost 100% agree with what you just said. Yeah, that's the thing, right? If you don't have any data and if you're just in a new environment, what the types of guarantee we can get, that's probably not. So yeah, I do agree with you in a sense that we need to assume something. But I guess my question is more like, what are the different types of guarantees with like different types of assumptions? So this is actually the open problems I was trying to mention, but with like different types of assumption, you get different types of the guarantees. What would be the like one layer like above you of getting the best combination of these guarantees and system? If you know 100% know your system, like two body problem, spacecraft. I mean, you design a spacecraft, so you should know the physical properties of your spacecraft, right? So you do know the dynamics. There, model based guarantee is probably what you need. You probably don't need a data driven guarantee. So depending on what you have, what's the strongest form of the guarantee you can get is um, first part of my answer. The second part is about generalizing the assumptions. Right? For example, if you think of like LLM-based decision making, the data they process is like not something numeric. So in our head, if you think of operating a robot on a planetary surface, we casually think that it's similar to Earth's surface. But what do you mean by similar, right? So here we are also defining the metric of like similarity, like when I speak the same sentence in Japanese and English, it's similar, right? But it's not in like a Euclidean sense. So with the same assumption, by defining like similarity in a different way, we can kind of make it look like kind of a non-exchangeable scenario. We are still using the same mass, but we are providing guarantees for non-typical data-driven systems. So, but yeah, going back, I agree with you like 100% that it's impossible to provide any sort of guarantees without assuming it. Yeah, of course. You have a question? Yeah. Okay, so can you point me to the bird you're referring to? For recomponent prediction? You mean this? Uh, this. So this. So yeah, this is here we are just picking delta. So for example, I mean the higher the better, right? This is like the lower bound of the success probability. So the higher the better. So let's pick delta to be like 0.1, 10% of failure. Then you trap that in, and you get the number from here. So based on the probability you pick, so if you pick a small delta, you get the looser bound. If you pick a bigger delta, you get a tighter bound at the expense of like a stronger failure. Was that your question? Yeah. Okay. Oh, okay. Yeah, actually I yeah. Let me just I don't wanna steal your time that much, so let me just conclude. Thank you for the nice questions. And my conclusion, I already kind of said it, but it's about the guarantees, but there are the different spectrum and the guarantees. So we search from like a robust guarantee, assuming that assuming something about uncertainty, and then we move on to something that is adaptive. So we adapt to like the uncertainty with the known structure, and the final layer is about adapting to the uncertainty with unknown structure. So with all these three layers, at least we can cover a bigger spectrum of nonlinear dynamical system. Also, definitely it's not all. And then now we have tons of open problems, as like a lot of you pointed out. We have like lots of open problems. We still have assumptions, right? And also, what are the guarantees? What are the best guarantees we need? Although I had an example where we use the model-free reinforcement learning for robots, but we do actually know the dynamics of the robots, right? It's just the joint dynamics, there's like Lagrangian, and you can just basically derive the equation of motion
And what are the best combination of the decomposition in the first place? That's kind of the question we are kind of ignoring throughout my presentation. What is your nominal model? What is the best nominal model, and what is the best answer? Right? You could linearize a system, something, or designing something, right? But this just an engineering kind of ad hoc choice. So there's autonomy, right? Something autonomous is still lacking in designing the system. And depending on the system, it's right the function. So you have a system, you have an uncertainty, and you get the guarantee. So there's a mapping going on. And that what's the best mapping depending on your scenario, depending on your emissions. That's missing. For some people, deterministic guarantee could be a must. Then what types of the systems? So we can kind of restrict the region of operation based on what they want. So these kind of a meta perspective is what's missing. And by generalizing the guarantees, thinking about all different types of the assumptions, we are trying to answer this question. Is one of the biggest, I think, open problems. And of course, how do we kind of generalize this to more modern tools, including systems with like different types of data, non-numeric data? That's also a question. Yeah, with that, let me conclude. And there's an email here. If you want to say hi. But yeah, thank you for, and I need to thank Keist for making this house possible, and thank you for giving me an opportunity to talk. All right, yeah, that is it. Thank you for listening.